Good morning, FOR 345. It's time for soil aeration and temperature. I'm here in the cloud city of Bespin, just before the Jedi Council meets, and before they meet, I thought I'd get this lecture in. So, this is getting near hunting season, and so I have one of my favorite hunting comics, as you might see, and so when the duck hunter is hunted, or this is what happens. Well, this week we are doing soil reaction, and so we're back in B13 Marshall after our cation exchange. And remember, the exam is Wednesday. If you aren't remembering that, then you're in trouble. So the exam will be Wednesday morning. Show up on time, even a little bit early, get to your seat, and we will get the exam to you. So what did we do last time? Last time we were finishing up soil reaction. Actually, we're kind of in the middle of soil reaction. And we'll need to fill this in Wednesday after class to finish up, but I wanted to start aeration and temperature now and let you get through the soil reaction lab. All the stuff that we did last week should enable you to get through that lab fairly easily. Well, I wouldn't say fairly easily, but if you have prepared and gone through your notes and you've gone through the web links, this will make a lot of sense. We'll tie that up next Monday in the lecture, and then we'll be completely done with soil reaction. That'll kind of push us on to nutrition, and that's where we're going. So now we get to soil atmosphere, soil temperature, and first we talk about aeration. And so to think about aeration, think about what the soil air composition is. And so we can compare the soil atmosphere with the atmosphere above it. And the three major gases, nitrogen, oxygen, and CO2, and look at their concentrations here in the atmosphere. Nitrogen, 78%, oxygen, 21%, and CO2, about 390 parts per million. You also know that as 0.039%. You should be able to easily convert that, right? Parts per million from parts per hundred. Okay. Well, what are the other gases? Well, there are small gases. There are many microgases, but they're on small concentrations, things like methane and hydrogen sulfide and so forth. But these are in small concentrations. And while they're important from a greenhouse gas point of view, in terms of soil aeration, we focus mostly now on O2 and CO2. So let's compare the air in the atmosphere to the air in the soil. So if we look at nitrogen, it's about the same. It's about 78%. The oxygen concentration, the partial pressure concentration of oxygen in the soil atmosphere is lower than 21%. Now, I'm not going to put an exact number on that yet because there are some factors we'll talk about that influence what that number is. Carbon dioxide, the number in the soil is higher than that in the atmosphere. It's higher than 390, and actually now we're up to 400 parts per million. And so again, the number is very much dependent on the number of factors, the things that we'll talk about in this lecture. So this sets the stage for us to compare the soil atmosphere with the atmosphere above the soil. So let's think about aeration. We need to define a construct and define this concept of a well-aerated soil. So a well-aerated soil is simply one where the gas exchange is rapid enough so that oxygen is replenished and the buildup of CO2 is prevented. So that's our definition. A well-aerated soil, gas exchange sufficiently rapid to replenish O2 and to prevent the buildup of CO2. Very simple definition. And from this definition will flow our understanding of what these soils are, how they're aerated or not aerated. Now this fits in really nicely with physical properties, so this follows well on the heel of physical properties. Okay. So let's think about field soil oxygen. What's happening out there? What is the concentration? What regulates it? What constrains the availability? And so we'll look at the number of factors that constrain this availability in the field of soil O2. Okay. And the first one, soil macroporosity. And we know macropores, we just completed the soil water exercise and we actually calculated macroporosity and the soil moisture characteristic allowed that. And now we'll kind of think about that on the other side. So if the macropores do not hold water, okay, there's our exchange of air. And what affects macroporosity? And we go back to physical properties and we're at soil texture and soil structure. Okay, so fundamentally this is a really big piece, a big control on this aeration, and oxygen availability is directly related to this. Okay, so that's our first factor. Our second factor is the flip of that, right? Soil water content. And remember our ideal situation, that pie shape, where we have 50% of the pores filled with air, 50% filled with water, macropores, micropores, and they are the inverse. So again, a soil pore is either filled with air or it's filled with water. And then we think about air-filled porosity. And so those are the static pieces. Now what's going on, we've got a dynamic system, and going on all the same time is the oxygen in those pores, in these macropores, the soil atmosphere. The oxygen is being consumed. Who consumes it? The roots and the soil organisms, the aerobic organisms, require oxygen for respiration. Okay? And remember that respiration, aerobic respiration, is so much more efficient than anaerobic respiration. How is gas exchanged in those three? So there are two ways we move gas around: mass flow and diffusion. And I have diffusion as the larger one because diffusion is the primary mode that we're talking about for the mechanism of gas exchange in the soil. Mass flow, what is mass flow? Mass flow, when wind movement or massive movements of air, pressure changes, that's aeration, that's exchange of gas by this physical movement. Diffusion is an exchange of gas by action, reaction against a gradient. And so we'll kind of look at that in terms of a picture. What is diffusion? Okay. So here's a picture out of the text, right? It shows the concept behind diffusion, the movement of molecules against a gradient. So we have on top the atmosphere, okay, and we have soil pores, and here's the soil interface. This dashed line represents the soil. And it shows the concentration. So this shows a large number of O2 atoms, okay, gas molecules, and these are a fairly high concentration in the atmosphere, and that would be 21%. And this illustrates CO2 partial pressure. This illustrates the number of molecules of CO2 in this relative picture. So there are a few CO2s and many O2s. We look down the soil, and there are many more CO2s and many fewer O2s. And so this is a gradient. The gradient flows from high concentration to low concentration. So that's diffusion. Okay? And so we have oxygen moving into the soil because the partial pressure, the concentration is greater in the atmosphere, moves into the soil. And the reverse is true for carbon dioxide. Carbon dioxide concentration in the soil is higher than in the atmosphere, and the gradient is moved to high concentration to low concentration. Soil air is ridding itself of carbon dioxide. And again, this is in response to a gradient. And so this is the process. And this happens in air-filled pore space. That's why we introduced air-filled porosity. And look at the rate. So the rate of diffusion is 10,000 times greater in an air-filled pore compared to a water-filled pore. Essentially, water-filled pores restrict this aeration. So we've got to have air-filled pores. Brings us back to macroporosity. Okay, that's the mechanism, and let's think about assessing it. How would we quantify soil aeration? And there are a number of things we can measure to give an indication of soil aeration. And so the first one we'll talk about is the concentration of oxygen and other gases in the soil atmosphere. Okay, the number that restricts plant growth in most upland plants, and note that's in most upland plants, there are anaerobic tolerant plants, but for the most part, the upland plants, when you get below 10% volume, that is 0.1 liter of oxygen per liter of soil, okay? Below that number, we are in a trouble and plants don't do very well, okay? So that's one way. So a well-aerated soil has an oxygen concentration of greater than 10%, okay? So that's a cutoff. That's one measure of aeration. The other side of that is carbon dioxide. So carbon dioxide is the reverse. So when carbon dioxide exceeds 10%, it exceeds 0.1 liter per liter volume of soil. This is toxic. Okay, so 10% concentration of CO2 and above, that's toxic. So 10% oxygen too low, less than 10%, 10% oxygen above, too high for CO2. So these are measures, the content of these gases, of aeration. So again, thresholds, if you have a concentration of carbon dioxide above CO2, poorly aerated. If you have a concentration of oxygen below 10%, okay, poorly aerated. Let's look at another one. Let's look at the air-filled soil porosity. Okay? And this looks pretty close to the volume of soil oxygen-filled. And why is that? So air-filled soil porosity, less than 20% of the total pore space air-filled. Okay? That reflects a problem. Okay? Less than 10% of soil volume. And why is that? This should be familiar. If we think back to our diagram of the soil, the ideal soil having 50% pores, half of those pores filled with water, half of those filled with air. So if we think about this as total pore space, and if 20%, less than 20% total pore space is in trouble, and if half of those are air-filled and half are water-filled, that's where this 10% comes from. So this is a threshold back-of-the-envelope calculation for aeration. If you have a soil with less than 20% air-filled pore space, you're likely to have a poorly aerated soil. Or you can express that in terms of the soil volume, because about half of those would be micropores in the average sense. That would be bad. So plant growth is inhibited. So now we have two things. We have concentrations of carbon dioxide and oxygen, and we have this air-filled soil porosity, two variables we can measure as an indicator of soil aeration. But there are more, okay? And so we'll go through them. We can also look at the rate of oxygen diffusion, and the so-called, titled the oxygen diffusion rate, ODR, oxygen diffusion rate. And here's the number, here's the threshold where top growth ceases. 0.3 of a microgram per centimeter square per minute. So this is a diffusion rate. It is an amount, microgram, a unit area, centimeter squared, per unit time. It's a rate of movement of a certain amount of gas over a certain area over a certain time period. So when you get below 0.3 of a microgram per centimeter per second, per minute, top growth ceases. So here's another measure of a poorly aerated soil. So poorly aerated soil is one which has a oxygen diffusion rate less than 0.3 of a microgram per centimeter squared per minute. Okay, that's three. Okay. We can also consider root growth. Okay, and root growth is pretty close. You know, it's 0.2 micrograms per centimeter squared per minute. So you're in this range, and you're going to lose growth. Enough said. How do you measure oxygen diffusion rate? Well, we can use it on a platinum surface and with a little bit of electricity. And so the rate and these are actually pretty tricky to do, to get these in the soil, because these are influenced by pH, and it's a tricky measurement. But nevertheless, you can insert these platinum electrodes and measure the rate of oxygen diffusion, and the rate of diffusion will change electrical conductivity across it, and translate that into a measurement of diffusion. Okay. So that gives us another way. So now we're looking at gas concentration, we're looking at volume, and diffusion rate. So we have three different numbers, three different variables to assess aeration. And so I'm going to ask you to know these, because this will be a key to understanding or expressing or quantifying diffusion. And again, this is part of productivity. Aeration, a well-aerated soil, is going to contribute to our concept of productivity. And we're building on soil physical properties. Okay? So these numbers, this set of numbers, these thresholds should be committed to memory. Okay. What is some data? So I have a colleague at University of Georgia that has a couple of grad students that tried to assess aeration for a couple of systems. Okay? And this graph here, okay, shows a percent response either to root or biomass. Okay? And this shows oxygen diffusion rate. And this is grams 10 to the minus 8 per centimeter square per minute. Okay? Note the log scale. And there are two systems here. Okay? Loblolly pine seedling emergence. Okay? And that's represented by these orange, I guess these pink squares. And it's pretty linear related. So once you get below a very small number, look down here around 10, 12, 0, you're getting to essentially no response. So if you look at the response of percent of loblolly seedling emergence, it's 0, okay, around here. And as the oxygen diffusion rate goes up, the success or the response of those seedlings goes up. So that's quite an interesting system, and one way to look at that. Okay? We can look at another system, a totally different system, and look at that in terms of cottonroot biomass. And the same kind of thing. So cottonroot biomass expressed by these wonderful, wonderful blue diagrams. And you see the same, actually this line should have been over here. Somehow I stuck that line over here. At any rate, it's the same linear relationship, so the slope is about the same, right? And this again shows the linear relationship of a totally different system. The cottonroot's biomass increases as the oxygen diffusion rate increases. So both of these are indoor pot studies and lab studies, but they show the importance of oxygen diffusion rate relative to productivity, whether you measure it in seedling emergence or whether you measure it in cottonroot biomass. Okay, so there's a fourth way, and we can actually measure the redox potential, the oxidation reduction potential. And this is called EH, okay, capital E, small h. And this is a number, it's measured in volts or millivolts, that expresses the tendency of a system to reduce or oxidize, hence the term redox potential. And again, potential, it's measured in volts. Okay? And so how does that work? Oxygen accepts electrons, and oxygen is becoming reduced. So when this occurs, we can measure this, the change in voltage, we can measure this potential, okay? And describe that as a tendency to reduce or oxidize. What's the reaction? Okay? O2 production, O2 absent. So when O2 is around, system will oxidize. There are plenty of oxygen. Oxygen happily accepts electrons. Okay? What happens when oxygen is depleted? Okay? In that case, something else has to accept the electrons. Okay? Something else. And this is the absence of oxygen is called anaerobic conditions. Okay? Poorly drained conditions lead to absence of oxygen, and other substances accept electrons. Where do the electrons come from? Respiration. Right? So even in aerobic systems, not even in, but in aerobic and anaerobic systems, the biota are producing. As long as you have oxygen around, respiration kind of proceeds unimpeded. But when the oxygen goes away or becomes limiting, aerobic respiration stops and anaerobic respiration goes on. So glucose is broken down. Remember glycolysis, and if you took some chemistry, organic chemistry, biochemistry, this produces energy, and it's broken down to pyruvic acid and hydrogens. But one of the things in breaking this down, this is the beginning of an electron chain. Okay, these electrons have to go somewhere, or else the process stops. They transfer down the chain. So let's look at what happens with this redox potential. So here we have a graph, and this is out of the text, figure 7.5, and it shows electron redox potential, EH, and this is measured in volts, okay, and it goes 0 to 0.6. Okay, you could express these in millivolts by multiplying by 100, by 1,000. Okay? And note what happens. This is days after saturation. Okay? So what happens after you saturate a soil? Okay? All of a sudden, immediately what happens is the plants and microbes, they take up all the dissolved oxygen, and it drops tremendously. So here we saturate, okay, and we're looking at DO for dissolved oxygen. Okay? And the dissolved oxygen is showing over here on the right, okay, and it's milligrams per liter. And over here on the far right is a pH scale. So note what happens to this dissolved oxygen. It drops precipitously from about 6 milligrams per liter as the plants, and then it kind of stabilizes because there's pretty much none left. It's depleted. Okay? And what happens to the EH? The EH, the potential, drops precipitously. So well-aerated soil, high EH, 0.4, and then as the oxygen is depleted, the EH drops very low to 0 and even goes negative. Okay? And if you look at that, that's pretty highly correlated with dissolved oxygen. Okay? And everything below this line is anaerobic, and it's called reduction. So iron is oxidized below this line. So as soon as oxygen is depleted, okay, iron is reduced. Iron is now getting the electrons that oxygen would be, but there's no oxygen to get the electrons. At the same time, notice that the pH goes up. Okay? So this will come into play later. The pH goes up. Here's some data from the North Yorkshire Valley peat bog, and shows a very similar thing, some data that shows EH and ODR. So these things are related. So we've measured the aeration. We've kind of expressed that with several variables. We've expressed it with electron, with this potential, with EH. We've expressed it with ODR. We can also express it with total porosity. And as you might expect, all these things kind of flow together. So if you look at EH and you look at the oxygen diffusion rate, they're pretty highly correlated. And so as the EH increases, you get more positive. Okay? The oxygen diffusion rate increases. And remember where the problem area is, it's around 0.2 to 0.3 micrograms per centimeter squared per minute, so right around here. Okay? So what's happening with this system? Okay? So we've got iron now getting the electrons, so let's take a look at this. Okay? So here's iron plus 2, okay? And in water, and we go to iron +3. So this is oxidation, or is it reduction? You go from +2 to +3. That's oxidation. Okay? So these electrons go to iron. So iron is getting electrons. Next up on the ticket, we look at oxygen in the system. So we add oxygen in. Okay? So oxygen receives the electrons. Okay? So if oxygen is getting electrons, okay, this is reduced to water, and this is what the system looks like. The electrons are going to oxygen, so oxygen is getting reduced. Okay? So plenty of oxygen around, the system is oxidizing, but oxygen itself is reduced. Let's put those two together, and if we have FeO, and we go to FeOOH, and we add in the oxygen, here we go to FeO, and a half of oxygen, and we oxidize that to FeOOH. Okay. What's another way to measure aeration? This is a clever thing called IRIS tubes, and IRIS stands for Indicator of Reduction in Soils. Okay. So these are tubes, and they're painted with an iron oxide. Okay. And when you put these in soils, okay, and they're reduced, that gets rid of the iron. Okay. So these are pretty neat. So this was developed by some colleagues down at Maryland, and thought that would be an easy way to look at oxidation and reduction. So if you reduce iron and peel it off, you'll kind of make it disappear. This is an iron paint, right? And if you put this in a reducing system, it will be peeled off, and it will undergo this reaction and become soluble and be reduced. And this is a visual picture of reduction. That's pretty cool. Okay? That's pretty cool. And then you can get a little bit more, let's say, clever, and you can actually measure the relative area of these with some sensing, some camera sensing, and then get an index of reduction. So this was done. So here's a site at Montezuma, and this is a site of the wetland meeting about 4 or 5 years ago. And this, of course, you can see this is a poorly drained site. Right? It's flat. It's anaerobic. It's a wetland. And there's clearly reduction going on here. So these tubes were installed, and those tubes that you just saw before went into this site. And the result of this is that iron is reduced. It then doesn't stick. The paint peels off, and you have an indicator of reduction, the IRIS tubes. Okay. You can do the same thing with manganese. Okay, so manganese also can be reduced. It can accept electrons. And this is what manganese coatings are black. Okay, and you can see what happens to these manganese coatings. These start out with a real painted black all the way down, the manganese coating. And you look at this, and all this manganese is gone. This occurs within a very short time. So this is the visual manifestation of reduction by the fact that this reduced manganese peels off and dissipates from this painted PVC. So again, another very clever thing, these MIRIS tubes for manganese and IRIS tubes for iron. And we go back and remind you that these were placed in this situation. Okay? These were placed in the situation of, I can't go backwards, that's all right. These were placed in the situation of that picture from Montezuma, this wetland. Okay? Here, side by side, the MIRIS tubes and the IRIS tubes. Okay? Now, if we go to a well-drained site, look at the difference. Okay? There's plenty of oxidation. Manganese isn't reduced. And what a nice change, right? You have these beautiful manganese coatings that stay. So that's a contrast. So the difference between this and the previous slide with all this white, exposed white, where manganese, reduced manganese dissipated, or left the PVC, again, a visual picture of reduction. So let's tie this back again to our EH value. And we showed you a slide showing about 0.4 when we had no problem with dissolved oxygen, and then it went down from there. So here's the EH slide and we'll go down and look at the elements that accept electrons as they're depleted. So we'll start with oxygen. Okay, this is the oxidized form. This is the ultimate electron acceptor in a well-drained system. Okay, when oxygen accepts those electrons, I showed you the slide before, that it is reduced to water. So oxygen converted to water. Now when we're starting to deplete oxygen, okay, and this starts to run its course, the EH changes from about 0.38 to 0.32. So as you're depleting oxygen, EH is dropping. Okay? Okay? It's dropping from 0.38 to 0.32. Now eventually all that oxygen, dissolved oxygen, dissipates. It's all reduced. What happens next? The next thing in line to receive electrons is nitrate, NO3 minus. Okay? NO3 minus begins receiving electrons. There's no oxygen left. So nitrate starts to receive electrons. Nitrate is reduced to nitrogen gas, N2. And this occurs in the range of the EH of 0.28 to 0.22. Okay? And these are volts. Right? Eventually, all the nitrate is reduced. And when all that is gone from the system, and you still have anaerobic respirations, the electrons need to go somewhere. And the next thing in line to receive it, in terms of the electromagnetic spectrum, is manganese plus 4. Okay? Manganese plus 4 is then reduced to manganese plus 2. Okay? You're decreasing valence, you're reducing. The EH value of this change, when this happens, this reaction happens, is 0.22 to 0.18. And eventually, all that manganese is reduced, and iron is next in line, Fe plus 3. So remember, manganese, you can visually see this by those MIRIS tubes. And iron plus 3 going to iron plus 2, we visually saw that by these iris tubes. And the EH for that value is 0.11 to 0.08. Now eventually you can go through all the iron. Okay? If these anaerobic reactions keep going, there's no more oxygen in the system. And then we end up with sulfate. So sulfate's next in line in terms of electronegativity to receive electrons. And sulfate, SO4 minus 2, is reduced to S2, the gas. And S2 combines with hydrogen sulfide, so you get the sulfide. And you know when that happens, that begins to stink. It smells like rotten eggs. And the EH value for that is yet lower, minus 0.14 to minus 0.17. Okay? And you can eventually go through all the sulfate and get down to carbon dioxide, CO2. Now we're at a very low EH. Everything's been dissipated. And CO2 is now reduced to methane. And you know methane, those little gas bubbles that bubble up in some of these swamps, you're looking at the process of anaerobic respiration, generating electrons, those electrons being accepted by carbon dioxide and converting that to methane. And that's yet lower, minus 0.2 to minus 0.28 volts. So we can use these numbers to estimate the aeration status of soils. And so if you ask, what is the question, ask what is the value of EH that is typical of a well-drained soil, we say it would have to go above that point where we have plenty of oxygen to be reduced to water. And so the EH of a well-drained soil is somewhere between 0.4 and 0.7 volts. Okay? So this should make a lot of sense. I mean, this series should make a lot of sense, right? We start out with oxygen. We're in a well-aerated soil. We run out of oxygen. Nitrate is reduced. We run out of nitrate. Manganese is reduced, and so forth, till we finally get down to CO2 and reduce that. And so that's why in some of these anaerobic wetlands, you'll see bubbles of methane coming up. You'll smell this hydrogen sulfide smell. You'll see all this reduced iron. And this is why it happens. It's the successive transfer of electrons down to molecules that are successively more and more reduced in a very anaerobic system. Okay. Now we've got numbers, we've quantified it, we have 5 ways to quantify it. And now let's think about the factors that affect soil aeration. Let's think about this in terms of the soil. Okay. So we'll move on to this idea, now that we can quantify it. So we think about what's the first thing, and we think back to our graph of well-aerated soil, and macro porosity and air-filled pore space. And so we have to start, it's macro pore space. It's the amount of space that doesn't hold water against gravity. And we said in physical properties, that was affected or impacted by soil texture, aggregate stability, bulk density, and organic matter. Okay. All that kind of agrees and should line up really nicely with what we talked about in physical properties. So this add-on to physical properties is the next big connection with productivity as we go barreling toward the end of the course. And so macropore space, and we've already talked about those in terms of soil physical properties. We've talked about texture, sandy soils. We've talked about aggregate stability. We've talked about those nice, stable, water-stable aggregates and granules. We've talked about bulk density, lower bulk densities. And we've talked about organic matter, which has low particle density and which contributes to structure. Okay? So those are the physical factors that contribute to macropore space, and that's governing aeration. Again, macropore space, more macropore space, better aeration. And the other part of that is depth in the profile. So as we go deeper and deeper in the profile, the bulk density increases, the pore size distribution changes, we lose those macropores and those large megapores, and the aeration becomes less good, let's say, or becomes poor depending on, it can even become poor depending on these factors. Okay? And so that's the physical part of that. The biological part of this is the rate of biochemical reactions. So what's going on? What's generating all this respiration? And largely it's microbial activity, decomposition of organic matter that's using up all this sugars, converting sugars to CO2 and driving systems. Okay? There's microbial decomposition, fungi, all these guys. And then what else is going on? We have the root system. Okay? And so roots and organisms, they're generating CO2. So there's a lot of CO2 being generated. So as these rates increase, the macropore space, the rate of exchange, has to rise to meet the occasion. And when it doesn't, the soil becomes poorly aerated. So these two factors, macropore space and biochemical reaction rates, are kind of driving some of this aeration. Now, if we look at this and we think about biochemical reaction rates, we've got to throw in season, right? And for obvious reasons. We have a lot of biological activity in the growing season, and we have a lot of biological activity, and when you get away from the growing season, things slow down. So we can think about this in terms of a seasonal nature, and we can explore that. We can think about this, and maybe a good way to express this is carbon dioxide in a corn system. Okay? So let's look at what happens from this illustration from the text. Here's data from a cornfield in Missouri, okay? And it's seasonal. So we go from June to August to September, November. So basically we go through the growing season into the fall season when growth stops. And we're looking at this by depth. So on the axis, the y-axis, we have depth in centimeters. Up here at the top, we're at the surface, and we go down 10, 20, 30, down to 50 centimeters depth, half a meter. So if we look at what's happening in June, and we see what's the pattern of CO2, so this is CO2 concentration. This is a cornfield. It's about 0.3 to 0.5%, okay? And it increases with depth. So this should make sense. We've got a lot of biological activity. As you increase with depth, the macropores dissipate, and things are just getting going, and the concentrations are starting to get high, and much higher with depth. Okay? As we go into the height of the growing season, the summer, when those corn roots are really putting out, okay, look at the pattern change. Okay? Now we're at the surface, we're 2 to 3%, 3 to 5%, and we're increasing with depth tremendously. Right here in the middle of the root zone, we're greater than 7%. Okay? And it drops a little bit, so it's really highly concentrated there. Okay? 7%. How much more higher than atmosphere? So this is a question, a take-home question. Okay? So the atmospheric concentration is what, 400 parts per million? So I'm going to ask you on an exam, perhaps, to be able to tell me how much more is the concentration in the corn of 7% relative to this 400 part per million in the atmosphere. Okay. This is a pretty astounding number. Let's go on with our season. We move into August, okay? And note what's happening. So August, the plants are starting to fruit, all the corn's coming out, root growth is dissipating, all that net primary productivity is being directed toward the above ground parts. Okay, root growth is slowing down. The CO2 is starting to dissipate. So we're seeing the reduced biological activity in terms of the roots, and the numbers go down. Okay? And we're looking with depth. We still have rather high concentrations, 1 to 2%, increasing with depth, 3 to 5%, but they're dissipating quite a bit. And now we're getting a little lower in the very deep horizons. We get into September, and leaf fall is going on. The plants are dissipating even further. The level of oxygen is improving. The level of carbon dioxide is improving. And the CO2 numbers are going down because of diffusion. Okay? And they are starting to really dissipate 0.3 to 0.5%. And as we move into the non-growing season, we're back down almost to where we were in just before June. Okay, less than 0.1%, 0.1 to 0.3%, and 0.5%. So this shows a seasonal pattern with depth. It shows increase due to root biological activity, okay, and a seasonal pattern with depth, and it's a very nice illustration of the interaction of depth and biological activity. So that's pretty astounding, and so that's a corn system. Let's think about a forest system, okay? And a forest system, again, we've got a corn system. Picture back to that slide I showed you in class with very little in the way of macropores, and let's contrast that to a forest system where we have just a tremendous, ubiquitous number of macropores, some 30% of the upper soil. Let's contrast this graph now with a soil system. Here we are from our Brook watershed. This is up in Maine, some work we were doing up in Maine on some of these watershed studies. And this a colleague, Ivan Fernandez, provided this data. So this is soil air concentration, microliters per liter, or parts per million on the left axis, and it's seasonal. And now we're looking at by horizons, and so we have the O horizon by this square, okay? And we go from March, we basically go from winter through a whole season, all the way to December. And we look at the O horizon concentration of carbon. Okay, it's very low, okay? Less than, it's like 3,000, 2,000 parts per million in March. Biological activity heats up, okay? Sorry, 200, it goes up to about 2,000 and drops down. As the depth increases, the next is the B horizon, so we'll go to the B horizon, the concentrations increase. So that makes sense. Concentrations increase with depth. The macropore space decreases with depth, the rate of diffusion decreases. And so then we go down to the C horizon, and the concentrations are higher yet. And in the peak of the growing season, just after root growth is peaks at around July, August, and then stops, and then top growth ceases. Here we have this peak. And so it's kind of neat to see the range of the height in the C horizon of about 4,000 parts per million, okay? And contrast that to the corn example, 7%. So a huge difference, okay? That's a tremendous difference in concentration of CO2 due to ag systems and forest systems, and that's directly related to the amount of porosity. Both of these systems have tremendous productivity, but the ability, the capacity of the system to dissipate that CO2 is much, much greater in the forest system. Again, consider that about 30%, 20% of these huge macropores, large animal-filled burrows, and that's all absent in the ag system. So this is a really nice contrast of forest and ag, both very productive. 400 bushels per acre of corn, or tons of biomass per acre, or even per hectare of the forest system, but a very different picture in terms of aeration. So you should be able to convert parts per million to percent. So what is percent? Parts per 100? Parts per million is 10 to the minus 6. Parts per 1,000, 10 to the minus 2. Order of magnitude 4. So I leave that to you to be able to convert percent to parts per million. And then how much more than atmospheric concentration? Okay, so remember the atmosphere, 400 parts per million, perhaps. So those are our numbers, and let's think about the impacts. Aeration can be good, can be bad, it can be positive, it can be negative, so I won't put a value on this, but we'll kind of consider what that means for some of our systems. So let's think about productivity. Root growth. Root growth itself, poor aeration impedes that. Okay, so we start getting above that 10% CO2, we start dropping below 10% oxygen in the soil atmosphere, and root growth is reduced. We drop below that oxygen diffusion rate of 0.2 centimeters, oxygen is reduced, and so forth. There are 0.2 micrograms per centimeter squared per minute. So all those numbers drop below them, and root growth is reduced. So it's not just the growth of the roots. So remember, the root is the uptake organ for the plant for nutrients and water. So that is diminished. So poor aeration, for most plants, reduces root nutrient and water uptake. Again, there are plants that operate in anaerobic systems, but for the most part, for most of our aerobic plants, this is going to reduce nutrient water uptake. Microbial decomposition, why does that matter? Well, the microbes are involved in releasing nutrients that are bound up in organic matter. So if we reduce the rate of decomposition, you reduce the rate of nutrient cycling, it reduces productivity. Toxic materials build up. What are some of the toxic materials? We talked about methane, we talked about hydrogen sulfide. Some of these are very toxic, and of course if you've got a plant and you're starting to put out a lot of methane, that's not doing anything for the roots, it's not contributing to respiration. Hydrogen sulfide, you're going to contribute to acidity. All these things that build up are not very good for plants, and CO2 of course is particularly not good. Okay. So some other impacts of poor aeration. Where do we go next? Here's an impact, and this is a very positive impact. I would say, this is a kind of a negative impact with a positive outcome if you're taking down trees. Okay? And so what do you do in a case like that? You're kind of up the proverbial creek without a paddle, but that requires a little bit of work. So when you get a contractor that doesn't pay attention to roots and compacts and poorly aerates, you have about a year or two before that is becoming history. What can you do about it? So we like to live in systems where we have engineered solutions. So one solution to poor aeration is to improve the drainage, remove the water. How do we do this? We use drainage ditches, drainage tiles, you can raise beds. Where did we see? We were in a field lab, we went to a field lab where we saw quite an effort to improve the aeration. Anybody remember where that was? It was the last field lab. It was at the DeSalvo Farms, where a system of ditches and tile drains in an organic soil converted a wetland into an extremely productive agricultural land. And that was made possible by ditches and drainage tiles, reducing the water table or improving the aeration. Okay. You can also play with the hand that nature gave you and just manage for the appropriate species. In a wetland situation, if you are managing a wetland, you're not going to favor aerobic trees, aerobic species, things like sugar maple and red pine. Okay, you're starting to look at things like red maple and some of the gums, some of the trees that can handle poor aeration. So if you have a little capital budget and a lot of land, you're not going to try and grow some of these species like red pine on a wetland. Okay? And so managing species becomes one of the better ways or the most sane ways to do it. As you have more and more capital budget, as you move more and more toward an urban situation, you can afford to invest more money in reducing the water table. Or in the southeastern United States, the loblolly pine forest and the coastal plain, just control of the water table made the difference between a non-productive, non-commercial forest and a commercial forest. And only dropping the water table by about 50 centimeters made a tremendous difference in wood productivity. And there's an economic return. Okay? So that was a little bit of an engineering. So here's what you can do for homeowners. You have lots of solutions, and most of those have to do with controlling water table and digging out and providing drainage tiles. So one classic way to do this around trees and a lawn is these little aerator tubes, these breather tubes. And note, this is a really nice, the wrong way to do it. This is a nice illustration because this actually plants the soil, it plants the root ball in a ditch that fills with water. Okay? You have to have enough room for the roots to expand and grow and enough room for water to move through. This is desirable. This is planting a Death Star, a death tree. So how do people aerate their lawns? Here's a little gadget that actually pulls out plugs. Okay? So this is an aerator for a lawn, and if you just compress the soil, you'd be changing the bulk density. So this gadget actually removes little plugs, and you drive this along, and it pulls out a small plug, and that creates a large gap, a macropore as it were, and deposits the soil, collects the soil, so that now you have a lower density and some artificial macropore space. So this is an enhancement for turf. So it's not all bad, and so we got to think there are positive impacts. There are places where aeration, poor aeration is desirable. Okay? And so we think about wetlands. And so wetlands are very important. We've discussed those in our lab. We visited a wetland that was now a cropland and talked about the implications of making that a cropland. So we need a definition for a wetland. So if you look in the official core definition, this is it. It's soils that are water saturated near the surface for prolonged periods when the soil temperature is above 5 degrees C. Okay? That sounds like a lawyer definition, right? It's kind of nebulous. Water saturated, okay, but near the surface. The question is, how close to the surface? Prolonged periods. What's a prolonged period? And another critical one that's pretty easy to see, temperature greater than 5 degrees C. So why 5 degrees C? Primarily because biological activity doesn't really get started until you hit that temperature. So if you have a waterlogged soil, no aeration, and the soil's cool, it doesn't really matter. And it doesn't matter until biological activity starts up and respiration begins. Hence this little piece here, temperature exceeding 5 degrees C. So that's the official definition, but we need more interpretation of it. It's just not enough for regulators or to kind of hang your hat on. Okay? So we start to think, what is a wetland? Wetland characteristics, there are 3 things used to define a wetland. The core, these are regulatory criteria for wetland. 1, that you have wetland hydrology, the water table is present. Okay? 2, that you have hydric soils. Okay? And say, well, I've got to define hydric soils. And 3, hydrophytic vegetation. These are vegetation that will grow in anaerobic systems. So let's start with a hydric soil. Okay, those are the 3 things. So you need 2 of the 3 to identify a wetland. Hydric soil, another definition. Hydric soil are soils formed under conditions of saturation, flooding, or ponding long enough during the growing season to develop anaerobic conditions in the upper part. Again, this is one of those, it sounds like it was written by a lawyer, and so it's insufficient for managers. So we need more information. Okay? So the definition of a hydric soil, while it's informative, is not really useful for establishing criteria. So now we have to look at indicators. What are indicators of hydric soil? Okay? Soils that are saturated and reduced. Okay, that's fairly easy. You can tell a saturated soil, you can tell a reduced soil, but how? Okay? We use hydric soil field indicators. So these are indicators that are based on soil morphology. Okay? And soil morphology is strongly impacted by reduction. Soil morphology is strongly impacted, and you can see it in terms of what accumulates: iron, sulfur, manganese, and carbon. So let's focus on these as indicators of hydric soil. This illustrates it nicely. This is an illustration of color, changing color, and organic matter buildup. So per aquic, per aquic is like a marsh. Aquic is a wet regime, reducing regime, and then we get to non-aquic. And note what happens. The organic matter buildup on these per aquic and aquic systems is very high. Okay? There's a lot of organic matter, a lot of carbon. The chroma is less than 1. So remember why that is? Why is chroma less than 1? Remember iron, the story of iron and the reduction? That reduced iron is gray, and a low chroma, and we talked about low chroma models. We also talked about chroma concentrations models. So this is a whole matrix, a gray chroma less than 1. Concentrations, modeling, chroma less than 2. Okay. So look in the wetland piece. These are pretty highly concentrated clay chroma in these hydric soils. And we look at nodules and concretions. So a nodule is a small, it's like a little BB, and a concretion is like a layered BB. Okay? And these form in poorly drained soils. And so these are the characteristics. These are indicators of hydric soils: high organic matter, clay chroma, some modeling, and nodules and concentrations. These are indicators. Remember low chroma? We go back to our Munsell color chart. Low chroma over here on the left, we have chroma 1 and 2. Okay, low chroma, these left columns. And remember, this is the U, 10R, 75YR, 5Y, the amount of yellow and red. And for anything on the lower left 2 columns is low chroma, these gray colors. And they have different expressions for different U's. And so you go to the Munsell color chart and you can identify low chroma. Here's an illustration. These are low chroma, this gray color. And that's too bad, pixelated here. And this gray, so this is low chroma. This is chroma of 1 and chroma 2. We have some modeling here. This is an indicator of a hydric soil. Should look familiar. Here's another indicator, oxidized root spheres. Okay? We have this clay matrix and this oxidized root sphere. So what oxygen is transported to these plants that have parenchyma cells, and that oxygen then goes to the outside. So just around that root where the oxygen is present, you get the oxidation or the color of orange compared to this gray color. So let's take a look at what that last picture is on a graph. Okay? So here's water. Okay? There's a slight bit of aerobic zone. There's a transition zone. Then this anaerobic zone is all that material, all that oxygen is dissipated. And here's what it looks like. The EH takes a big drop, goes to small numbers, so we know that indicates a poorly aerated soil, small EH. And remember, what's the reference? What's the EH of a well-drained soil, of a well-aerated soil? And we're looking at 0.4 and greater. So this kind of makes sense. It depletes with depth, the anaerobic zone. And we look at the root channel, and so you get this aerobic zone right around the root channel because oxygen is pumped out to the roots through these parenchyma cells. Then you get this oxidized iron, and then you have the gray around it. So this is a visual graph, kind of matches up with the picture on the previous slide. Here's where the red would be, here's where the gray would be. Okay? And it's superimposed on that, the EH, oxidation reduction potential. That's kind of cool. So where is all this information contained? So there are many hydric indicators and changes in different regions of the country. So we can give you this field indicators of hydric soils in the United States. So I have that linked on the website. So if you're interested in, you can check that out on the website and get it. It's a free download. You can also order it from NRCS. It's a pretty useful publication. And this is now what's used to identify hydric soils. So if you get involved in delineation of soils and hydric soils and wetlands, and some of you might do this for a living when you get done with your degree, doing these wetland delineations, you'll become very familiar with this book. And for various parts of the country and various types of the soils, there are a number of indicators, and they're all collected here. And they're continually being tested and updated. Pretty cool. Free your government dollars at work. So you might be a hydric soil if you have a depleted matrix. Okay? Here's a depleted matrix. It's depleted of iron, and it's gray. It's gray color. This is called depleted matrix, and it's a morphological indicator of color. Okay? Here is a sandy soil. It's glayed, okay? And the same result, this low chroma matrix, this is a hydric soil indicator, and so you see this condition, and you check off, yes, this is a hydric soil. And so kind of we tie this together and think about the soil moisture regimes, because I introduced the concept of aquic and peraquic. So let me back up and kind of define those regimes. Okay? Aquic moisture regime, aquic, wet, okay, this is a reducing regime. And so this describes a condition of no dissolved oxygen. DO stands for dissolved oxygen. And why? Because of saturation. Okay? So saturation deprives the pores of airspace. All the oxygen is taken up, and there's none left. And now we have an aquic moisture regime in a reducing condition. And this happens a lot seasonally. Peraquic. So this is where groundwater is at the surface. Okay, so it's, instead of a seasonal situation, this is continuous. Groundwater is always at the surface, and typically these are marsh situations. Do you know some other soil moisture regimes? If you think back to our exercise in soil water, our lab in soil water, you'll think back of several. We actually had a question on the evapotranspiration and precipitation ratio for several moisture regimes. And remember Utic, Eustic, Aeritic, and Xeric? Okay? And enough said about that, but we contrasted and compared the precipitation with the evapotranspiration in the soil water lab, and we defined those. And we looked at the number of days you need to irrigate. So I guess we should close with thinking about wetlands and why they're useful. And this kind of reinforces our lab that we had, the last field lab at the onion farm, DeSalvo's. So wetland functions, species habitat, water filtration, flooding reduction, shoreline protection, recreation, timber, food and fish. They serve all these ecosystem services, okay? And that's why we have our laws for Clean Water Act, that you cannot destroy a wetland without replacing it. These wetland functions are highly valued. Okay. So that pretty much closes, and I'll leave you with some words of wisdom. Is when I come back, we'll pick up the end of acidity and soil temperature. We'll kind of link that, and we'll move on to productivity. This is bringing us pretty close to the end of the semester, and the next thing we'll talk about will be soil nutrition, plant nutrition and soils, and that'll close the semester. And if we have time, we'll say a little bit about productivity and soil classification. And by then, it'll be thinking about the final exam and closing out the semester. So I'm leaving the planet of Bespin, and I hope you will be soon leaving Illick Hall. Have a great day, and I will see you Monday morning. Enjoy the lab this week. Have a great weekend. Goodbye from Bespin.